Okay, well, first of all, I also want to thank the organizers for this wonderful workshop and also the opportunity to talk about my group's work. I'm going to talk about living chiral crystal 2.0, and this is the work of an incredible group of students and postdocs in my group and Jorn's group. Two of them are actually here, Shreyas and Hyun. I would encourage you to go to their posters. They can tell you actually the nitty-gritty details of what I'm going to be talking about. And of course, Zerhan is here. He's the chiral crystal 1.0, so you can talk to him as well on the wonderful work that he's continuing to do in his group at UCSD. Okay, so I'm going to actually show you how distinct mechanisms of chiral symmetry breaking at the microscopic scale can actually give rise to the breaking of non-reciprocity at the macroscopic scale, and how that emerges in very different ways. You either can get basically displacement type oscillations in the phase space, or velocity oscillations, and this is kind of what we're going to try to unpack that and how that actually comes about. And I'm going to first take you to the wondrous world of what I call marine active matter. And what you see here is a tiny branch of the phylogenetic tree. Guillaume introduced this concept. So this is basically the echinoderm branch. Echinoderms are this exceptional group of organisms. They start from basically a bilaterally symmetric larvae, and then they develop into pentameral adult symmetry. I'm showcasing two species here. And they kind of like the way to think about them for all intents and purposes in this talk is that these are chiral self-propelled particles. The chirality comes in their dynamics, meaning that they can either have a rectilinear type swimming motion or actually a helical type swimming motion. And we will see that how that actually emerges in the dynamics of these systems. And because there's a concurrent program on moire physics, you can think of this in analogy to a periodic table of these active particles, chiral particles. And chirality is this new dimension. It's this degrees of freedom that can actually opens up the possibility of designing really interesting features at the macroscopic scale when you self-organize systems out of these particles. So this is basically particles or the embryos of starfish. You can see that they're kind of, this is looking at the top. They attract each other and they rotate with respect to each other. This is our new favorite model system. This is sea urchin. And here you can actually see that they're chiral swimmers. So they come together. They also have this alignment interaction. And what we're interested in is when you have this type of interactions at the microscopic scale, what kind of features do you get at the macroscopic scale? And the bulk of the talk will be focusing on starfish and the emergence of this active crystal structure, this active solid. And then at the end, I will just show a teaser of what happens when you have this type of chiral swimmers. And in practice, you can actually get even what I will call a p-adic liquid crystal structure. And the kind of like a punchline is that when you have a combination of time reversal symmetry breaking in the system, different mechanisms of chiral symmetry breaking, and of course this action-reaction non-reciprocity that have been discussed quite a bit, you get this intriguing, I guess, phases, new phases of matter at the macroscopic scale. Okay, so let's take a closer look at the structure of these starfish embryos. So this is a microscopy image looking at the organization of a very important organ, cilia. So first of all, note that these are ellipsoidal type structures. They have an axis of symmetry, which we call anterior-posterior axis, or the AP axis. And then you can see that it's rather homogeneously covered with these hair-like structures. So these are cilia. You can think of them as active polymers. They actively beat and they synchronize and then can generate fluid flow around these particles, which then causes these organisms to actually swim. And very interestingly, the swimming or the synchronization of this cilia is involved in induction of left-right asymmetry in many organisms, including us. So let's take a closer look at this box here so you can look at the dynamics of cilia. And you can see this is, again, the surface. There are many cells here. Each of them have one cilia. And you can clearly see this propagation of this metachronal waves going through. And then the fluid flow, of course, as a result, is moving. And these objects can swim. Now, we're going to look at kind of like the swimming behavior of these embryos. And just to orient ourselves, we're looking from the side, how they swim. And this is the water-air interface. The objects you see in the bottom are the actual embryos. And the top is just a reflection of them at the water-air interface. So let's look at the ones in the bottom. And what you can see is that these embryos, they can swim and they can come to the water-air interface. Let's first focus on this one. And they can attain a stable configuration such that their AP axis is perpendicular to the water-air interface. And then this kind of like is basically when you now look from the top, they look like spins. They rotate all in the same direction. And this is one mode of symmetry breaking in the system. But I also want you to note another type of behavior here, which is you can have embryos that come to the water-air interface, but then they have a finite angle with respect to this interface, and then they actually precess about this axis of rotation. This is kind of like orbiting. So this is another mode of chiral symmetry breaking within this system. And the kind of like the focus of this talk is very briefly, initially I'll mention what happens, what do you get from spinning degrees of freedom within this system. So you spin your material, individual particles within your collective. And this, of course, kind of like going to emerge as a non-reciprocal response at the macroscopic scale or odd elasticity. And then I will also show that this precision of axis of rotation, this type of orbiting, is going to give rise to a form of active gyroelasticity, which is not the limit of odd elasticity. It's actually an entirely distinct type of elasticity that emerges within the system. Okay, so we have this chiral swimmers, we have these spinners. What do we do with them? And we decided to put a large number of them together. And I think this video has been showed a few times, so I'm just going to very briefly show you that you can get a large collection of them. I mean, it's a very striking video. You can see a lot of them can come together to form what we call a living chiral crystal structure. And just so we're all on the same page, this is a millimeter scale bar, so it's very large scale phenomena. It's also, in terms of time, it's actually a process that can happen over days. So you really have the formation, growth, dynamics, and dissolution over a few days. So for each of these, processes, you have quasi-static, quasi-steady state at some periods of time. And again, one thing to note is that again within these collections, we have spinners in the system. And I also love to show this image because it gives you a sense of scale. So this is a 6-well plate. It's basically a few centimeters across. And you can clearly see that this is something that you can see with eye. So this is an initial formation, so it's very much like nucleation growth. And then, of course, these can come together and then form this large cluster at the macroscopic scale. Now, just talking about the type of microscopic interactions that we have within the system. So one thing we can see is that as the starfish spins, it pulls the fluid inward and it pushes it downward. So this basically generates an attractive hydrodynamic interaction between these embryos that then results in basically them coming together. And this, of course, is something that we can ascribe to a potential energy. But then you can also note that as they come together, this is at the interface. We have this ciliary interactions, we have hydrodynamic interactions at the interface, and that actually results to a second transverse force at this interface, which cannot be ascribed to a potential energy. And you can also see that basically when they come together, they don't stick, they actually start rotating, orbiting with respect to each other. So these are the type of microscopic non-reciprocal force and torque that we have within the system. And well, one thing I want to mention is that this is a generic feature of these type of swimmers. And in fact, it was initially shown by Ray Goldstein and Knut Drescher for the case of Volvox. And as long as you have these non-equilibrium properties, they can basically make this bound state at the water-air interface. Now, this, because you have this pre-stress that originates because of the transverse force exchange between these spinning embryos, what you end up getting, of course, is a global rotation, a chiral, broken global chiral symmetry, and hence we call this a living chiral crystal. Now, of course, this is not the most interesting mode that you have in the system. The most interesting mode is actually the most interesting dynamics that you can get is if you go to the co-rotating frame of the crystal. And under certain excitations, what we observed was that you can get basically this long range, long-lived oscillations or shear cycles within the system. And again, I want you to note the scale bar here. Both scale, but also time is actually more important. This is actually oscillations or this shear cycles can persist over hours. And of course, this is an overdamped system, so the presence of this was a total surprise to us. And again, which can really happen, of course, only when you are out of equilibrium. And this was kind of like at the same time, actually it was during the previous, in 2020, we had this program here at KITP on Zoom. That was really introduced me to this amazing world of non-reciprocity and chirality, and at the same time we came across this system and stars aligned, and that basically we started really delving more into the details of this. So I will briefly mention that these kind of like oscillations. So this is basically looking at the displacement gradient tensor, looking at the four principal components, and you can clearly see that you have these, plotting the amplitude as a function of time, you can clearly see that we have these oscillations. But you can also note that they actually decay because the color kind of like becomes lighter, so there is a decay. And the presence of this, we kind of like was a kind of smoking gun that because you have this microscopic non-reciprocal interactions within the system, you can actually get a macroscopic non-reciprocal response. And this is due to the work that was introduced by Vincenzo and colleagues, where they show that if you relax this energy conservation constraint in linear elasticity, you can get unexpected mechanical properties, and because you start getting new additional moduli, odd moduli within your elastic modulus tensor, which are off diagonal, and they can start actually coupling different degrees of freedom within your system. And that is basically, so this type of oscillations can, in principle, be attributed to the fact that you have an odd elastic material. Again, but we can, in fact, we started from we had a hydrodynamic model for our system. You can coarse grain from that, and then you can actually see that this actually gives rise to odd elasticity in the system. And again, I will emphasize that one feature to note is that they actually is transient, so they decay in time. Now, this was one looking at elastodynamics and see this feature of odd elasticity. But we also looked at odd elastostatics, basically by looking at topological defects within the system. You can have 5-7 defects within the system. And in fact, if you look at the strain field around the defects, and you parameterize this strain field using two angles with respect to the Berger's vector, the orientation angle, as well as the shear angle, again done by Vincenzo and his group. You can show that there's actually, it's modified with respect to the passive elastic solid because of the presence of this additional odd moduli within the system. And this was, for us, a way to measure the ratio of odd elasticity to the even or bulk moduli that we have within the system. So this was another second, I guess, way to show the fingerprint of odd elasticity in the system. Okay, so this was living chiral crystal 1.0. So I'm going to talk about what happened next. And we were really interested in this type of oscillation, so wanted to see how you can actually start exciting them. And then we started realizing that actually there is a whole new dimension to the system, which means that the system is not just two-dimensional. You actually have this third dimension. And as I mentioned, you don't have just spinners. You actually have particles that can tilt, and then they can precess about this axis. So you have these degrees of freedom within the system. And in fact, these are two modes of swimming for these embryos. So they have this basically rectilinear type swimming, but they also have maybe better. They also have this helical type swimming, and this kind of like translates then into basically having either a spin or this orbit within the system. And now, basically, when we started looking at kind of like oscillations, one kind of thing that we over and over was happening was that we would get oscillations like this within the system. So this is a crystal again, and what you actually see is that we don't get this same kind of transient odd oscillations, but rather we get velocity oscillations that are kind of have this bistable nature. So it looks like the system actually has two stable states, a fluctuating state and then an oscillating state. And it's easy to see this if we look at the region within this crystal, and then look at the average velocity, and then basically look at this phase space spanned by these two velocities. And then you can see that the system initially is oscillating, and then it switches to this fluctuating. It then switches into this oscillatory state. It's actually constant amplitude oscillations over very long periods of time, like up to 50 or more cycles, and then it relaxes back to this fluctuating state. So it has this kind of like bistable nature to the system. And one thing to also note is that this was looking at the average behavior, but if you look at, I'll just maybe quickly play this video again. If you look at there's actually also spatial dynamics of how this velocities comes about. So it's, you can see that initially you get actually a region that kind of like starts oscillating, and this region of oscillation starts growing and expanding and then taking over. And the same is true that it's after the oscillations, it basically shrinks down. So very much like a population of embryos that are doing some kind of dynamics are basically growing and then shrinking after this. So how do we understand this? And of course, for the longest time, even when we first observed this system, we were on a quest to be able to get the dispersion relation and do a mode decomposition of the system, because that can tell you a lot about the dynamics. And this was possible through a collaboration with Jorn. I'm not going to go into details. He's actually going to talk about. Yes, yeah.
On the crystal in this phase, what do? It's a mixture of swimmers like this and spinners, or what?
Yeah, so I'm going to get to that, but actually what happens is that initially some of them tilt, and then this tilt propagates. So you actually have a propagation of a tilt angle within the system. And then kind of like, and then they can be like, so you have a bunch, I'll show you a video that you can show like the tilt actually kind of like oscillates, so the tilt angle also oscillates. So we think that they go into this other mode of like chiral symmetry, so orbiting, and then that's what you get. I'm going to show some, and then we can kind of like talk about this. Okay, so let me, yes. So this, David, yes.
So you've shown that we have sort of, we have spin, a biological version of spin,
yes,
angular momentum, and then also a biological version of orbital angular momentum. Is there some analog of spin-orbit coupling?
Absolutely. Yes, I'm going to talk about it. I will show you a sneak preview, and I'm going to ask you to go and talk to Shreyas. We're very excited about this. I think initially I said this is the periodic table of this talk, and I didn't mean that. And I think I was more serious about that, because I think these are really particles that kind of you can start thinking about these features and kind of how you can design actually materials out of this. So, okay, so yes. So let's look at, so we kind of collaborated with Jorn and his group, and we did a mode decomposition in this system. I won't go into the details of this because he will talk about this in detail tomorrow. I want to talk about the results. First of all, this is the embryo trajectories. And then we could use dynamic mode decomposition to actually get the spectrum of the modes. We're going to focus on a few low rank, basically low rank representation of the dynamics in this system, because it looks like it actually captures the dynamics quite well. So I'm going to focus on this few modes, but then actually it turns out that it's an incredible dispersion relations, I guess. Yeah, there's a lot of details there, and Shreyas can give you an overview of where we are trying to go with that and how we're trying to understand that. But getting back to this, we can see that, of course, we have a zeroth mode, this global rotation, and then we have about 7 modes, and these are basically the modes that are, this of course originates from this pre-stress that comes from the spinning of the embryos, but we have 7 modes that correspond to low frequency, long wavelength modulations within the system. So these are the acoustic vibrational modes that you have in a solid, and you can see them here. But then we also have 2 other modes that are, you can see them, they're actually kind of like tracing a circle. And this is basically consistent with having this precision dynamics when the crystal is actually oscillating. And of course, you can combine all of these together into a dispersion relation. And I'm going to first start from the fluctuating state. I think this is glorious. I love this because I've been wanting to do this for so long, and it just looks amazing. Because so what we are plotting is basically the real part of the frequency. I'll show you the imaginary part in the next slide, and then again we get
Nikta, just
yes.
Small. You said these are like the acoustic vibrational modes of the solid, but they're a result of oddness, not otherwise, right? These are not velocity beating against position. These are 2 displacement fields beating against each other, right?
Right, yes, yeah. I mean, actually, you can see that you get this quadratic dispersion relation, which basically is telling us that we have this consistent with 2-dimensional linear odd elasticity. So this is in the fluctuating state. So, the lines are the fit to the data, and it shows the quadratic fit. But then if you look at the oscillating crystal, what you can see that we still have this acoustic branch, but then these 2 modes actually are even at 0 wave vector, they have a finite frequency, and this is basically are these dissipationless type I guess modes that we have, and we kind of like very consistent with having this optical band within your system. But again, emerges not because of the structure of your crystal. I think this is a very unique feature. So usually, if you want to get this type of bands, you have to do something with the a triangular lattice. You have to do something with your lattice. But this comes from this orbiting degrees of freedom, this precision degrees of freedom algorithm that you have within your system. And again, of course, it goes away. And now, one other thing is we have both the frequencies, they have both the real part as well as the imaginary part. And one thing to note is that the kind of like the ratio between the imaginary and the real part actually gives you the ratio between odd and even moduli within the system, which when we look at it this way, it's actually very consistent from what we measured from looking at the just the structure from the defect strain fields. And what it shows is that even in the fluctuating state, the crystal is in the active odd regime, so it's an odd elastic material, and cherry on top of that, it can also switch into this oscillatory motion. There is a lot of things we can do with this. How much time? Oh my God, okay. There's a lot of things if you want to do this. I'm going to just very briefly mention that this has opened up the possibility for us to look at mode-mode coupling. I mean, this within the system, either spatial or anti-symmetrized temporal correlations. This is something that my group developed, so we can look at non-equilibriumness within the system. This type of spatial couplings can actually allow us to think about spin-orbit coupling within the system. These are, of course, the low modes. I guess Shreyas can tell you about what you actually even get nice, opening of the bands and other things, but I'm going to skip that. And what it means is that if you now construct the dynamics using and note that optical modes and acoustic modes are actually separated, they're not coupled. But if you actually construct the dynamics from these modes, what you will see is that odd elasticity shows cycles within the strain field, whereas this kind of spinning, the orbiting actually shows cycles in the velocity field. You don't get actually anything in the velocity field here. So that's, that has been, again, a way for us to think about how you can get work out of this system, because with odd elasticity, you need some kind of perturbation of the system to kick it and be able to get this type of oscillations. But you also have this mode, this basically completely different state, and you can get work from these states as well. Am I out of time, or? Yeah, all right. We have a theory that actually the only thing we kind of like needed to modify was to add this kind of effect of tilt and then precession, which basically comes about as an orientation-dependent self-propulsion. So going back to your question, Corentin, it's basically tilts, and then you get this self-propulsion within the two-dimensional, projection, and that's how you get. I'm going to skip this because I want to get to the most important thing. I mean, if you have a two-state system, the question is, can we excite the system to go from one state to the other? And can we actually have a level of control? And in fact, this is the case. So I'm going to show you experiments that they have designed, which is basically applying a uniaxial compression to the system. And then, of course, that kickstarts, transitions the system from the fluctuating state into oscillatory state. And it turns out that it's actually not all compression strain rates are equal. This is a Goldilocks situation, which means that if you are too slow or too fast, too slow, you're only exciting low wave vector deformations. Too fast, you are generating plastic deformation within the system. And it is in this narrow band that you get basically this type of oscillations that can persist. Okay, you can do this multiple times. Okay, I'm gonna, and there's a lot that we don't understand. So the system can interact with the boundary in very unusual ways. This is a video that we've been staring at sometime for quite a bit. We basically introduced boundaries within the system, and this is just a band that has been labeled, so you can see that you have this very unusual velocity profile within the system that forms. a lot of interesting defect dynamics, not just when it interacts with the boundary, but of course, motivated by David, or he challenged us to look at curved surfaces. We have a cone as well, but also look at basically concavity and convexity of the surface. You can look at how the crystal forms. And then lastly, I would say that we don't necessarily need to work with just one type. You can actually mix different types that are separated by some, basically they are siblings, they're just separated by some time, axis. And then you can start introducing more non-reciprocity within the microscopic non-reciprocity within the system. And that I'm going to encourage you to go and talk to Hyun, because you can get interesting features such as phase separation, phase coexistence, but also new phases. For instance, this is an example where we get chiral flocking that then transitions into a chiral crystal state. Okay, that is, I guess that's all I have, right? But I'll show this video, because now this is our new kind of particle of interest within the lab. This is sea urchin. You can see that it's quite different from sea star. And because of that, you can, I think we can get some very interesting features within this system. And I'm going to maybe end with this here.
All right. Thank you very much, Nikta. You have the first question.
Hello. Great talk. Can you comment on whether in the native ecology these effects are important or not, or these are like systems that are remarkable to study non-reciprocity or elasticity?
Yeah, so I think that's one of my favorite questions. So I can speculate of whether you can get this type of phases within the nature. We haven't seen them with our eyes, but these starfish, sea urchin, these are broadcast spawners, and they usually live in intertidal zones where you actually have very shallow waters, a lot of fluctuations. And very recently, there has been work from a group where they showed that if you have a group of embryos, not marine, this is actually frog embryos, together, they have a higher chance of survival. And they did this really nice experiment where they created a wound in one of them, and then and usually when you create a wound, you get this calcium signaling within one embryo. But they saw that actually there is a calcium wave that propagates through the whole collective. So it may very well be that it's kind of some kind of Ali effect. And I think this is, so I have some speculations of why you can get something like this emerge in nature and everything. But yeah, at the moment, that's yeah.
Well, let's alternate.
Thank you. Great talk. I have like a lot of questions. I'll
Please.
ask a very sort of quantitative one, maybe. Did you said these topological defects that appear inside your crystals. Have you looked at the density of those defects and how it changes between these various phases that you see?
Yes, in fact, what I will tell you is that when we started, it was very hard to get only one pair of defects, so we can do this defect strain field analysis. So we started actually looking at ways to do that by doing experiments like this, like kind of kick one out and then try to locally create defects. So there's a lot of defects within these systems. You also have chains of defects. And in fact, there's a very nice work from William Irvine's group. They looked at that quite extensively. I think, yeah, I think there's a lot of rich kind of physics there, and they also can come from the boundary. They can, so I think it's absolutely an incredible, I guess, arena to think about defect dynamics, and not just defect in structure, defect in the velocity field, defect in other fields as well, right? Yes, yeah, right. Yes, yeah.
Beautiful experiments. Just a clarification. I was trying to understand the mechanisms of the waves. So, do you need just a system of co-rotating spinners to generate the oddness waves, the kind of the fluctuations stuff, or you need additional ingredient to see them?
You need, so for the odd waves, we need time reversal asymmetry. So we need the activity or the time reversal asymmetry, and then we need this chiral the spin. So that those are the two ingredients that I think.
So you're saying if you have just a bunch of co-rotating spinors, active particles in the monolayers, one should see the waves?
I'm going to say yes, but I would say that probably is a question more for theorists. But yes, yes.
So maybe we should ask, because we have had simulations of spinors of monolayers, and we never saw waves. So I'm very curious about the mechanism. Thank you.
Oh, yeah, sure.
Rita, you showed two kinds of phase portraits: displacement against displacement and velocity against velocity.
Right.
Is the velocity an independent dynamical variable in this problem, or are you completely in the no inertia regime where the velocity is automatically determined by displacements? I was wondering also because the scale is not that small. So I mean, for example, in your velocity cycles, can't they be re-expressed actually as some more complicated displacement cycles or strain cycles, if you're strictly Stokesian?
Yeah, interesting question. So I would say that, for instance, you don't get velocity oscillations in the other example, right? But you do get, I think that's actually a very interesting question, something that I have been trying to think as well. But I would say that we don't get velocity oscillations for those. And I mean, here you can get, of course, because of the fact that, yes, yeah.
Shall I also go? Yeah, so in fact, these cycles, you can, coarse grain over certain regions of space. And within that region of space, you can plot divergence cycles or like the divergence curl cycles or some shear 1, shear 2 cycles, as well as velocity cycles. And what actually happens is that in the oscillating state, there are actually regions within which you only see velocity cycles and you don't see cycles in strain space.
But I'm still confused if there isn't really a dynamics of the velocity because you're strictly Stokesian. It should be re-expressible as displacement cycles of some kind.
Yeah, so I mean, I think the thing is that you have these additional degrees of freedom that come from the 3D orientations of the embryos, which give you an active forcing on the 2D displacement field. So yeah, but we can talk later.
Probably a related question. So, am I right that this oscillating state phase is synchronous state, kind of like in a chromotal sense, because it looks like that? So, in that case, am I right that you should have a additional Goldstone mode associated with that, in addition to being a crystal? Do you see that? Because it breaks the...
No. So I don't think... I think there's still a lot that we need to unpack about the modes and everything, but yeah, we can talk more. Yeah, right.
When you go from oscillations to fluctuations, it kind of looks like the oscillations accelerate. So is this something you can understand with the tilt thing? Like, it looks like they accelerate until they stop, right?
Yeah, right, yes, yeah. So I think it expands and then it basically, I mean, I guess it expands and then of course you have also the material, still have the material properties, you have the fluid and everything, and I think those dynamics will then lead into, yeah, I don't know if that's it. Right?
So we also observe that towards the end when those oscillations are stopping, the spin frequency of the embryos.
Oh yes, yeah, that's actually right.
And
yeah.
the precession frequency is sort of proportional to the spin.
Right. Yes. Yeah. That's so, actually yes. Yeah. Yeah.
Thank you very much for the talk. Really interesting. So I'm wondering, in the case you have a pistol and apply the external pressure, and what you observe is there is a peak corresponding to certain velocity, like the certain rate of the force, right? So I'm wondering whether if you make the force oscillatory also and make the angular velocity similar to the oscillatory velocity, can you observe a resonance effect?
Right. This is experiments that are currently being designed and hopefully done in the lab. Yes. Yeah. That's our hope, that we can actually kind of two ways actually. One is using this kind of like, I guess, oscillatory, I guess, excitation. But we also have two other ways. One is this magnetic kind of like the droplets. We think that we can actually do something with those. And very recently, we have also started introducing magnetic disks within these systems. And we think that there could also be possibilities of then locally create this type of, yeah, I mean, just some ideas, but hopefully, yeah.
Okay, thank you.
Transpire.
Great talk. I have maybe two ways of asking the same question. I'll start with maybe the more experimental one. So when you have these velocity cycles, it makes me think a lot about the lattices of Higgs bugs represented by Gustavo Monday. Also the pedestrians of like thing that Denis Bartolo also is working on, where you have like a displacement field and a polarization field. Mm-hmm. Do you know whether there's a difference, or it seems to me like the difference is from the fact that the Higgs bugs, they only start to rotate because of the interactions, but your starfish, they precess no matter what, I guess. So could you comment maybe on that?
I think there could be similarities. I would say that I think with this system, it's basically you kind of like they switch into this mode of rotation, and then locally you get kind of polarization in both. Like I mean, in like if you look at the third dimension, locally they start aligning, and then that kind of can. So yeah, there could be some local polarization also within the system. And in fact, if you look at the tilt, you can see that we have like this tilt. Yeah, so that's that I think yes could be. There could be some.
And maybe a more formal way of asking the same question is, what do you need for gyroelasticity? Like, what should the structure of the equations be?
For the gyroelasticity,
yes.
Right. I think it's just really this tilt dynamics that is basically. So it's not. I guess usually the overdamped limit of odd elasticity should give you gyroelasticity, but here there are two distinct kind of mechanisms.
So you have an extra field.
An extra field that actually giving rise to that, to this whole new. That's why I want to say it's active gyroelasticity, because it really comes from this active degrees of freedom within the system, as opposed to being the limit of odd elasticity itself.
Thank you.
Sure.
So, as you know, we recently published the case of the active Brownian particle with chirality. So it's just, has no alignment interaction, it just turns at different radius of rotation, right? And the linear elasticity theory shows these kind of collective oscillations that can occur, and in a finite system that could translate into collective rotation. And because this is mesoscopic and it's appearing spontaneously, in a finite system, you would also expect it to transition from an order to kind of like a disordered state. But that's where the analogy limit is. And here you have many other effects. You have the tilting, you have the hydrodynamic interactions, which I'm not sure how important they are at this point. So I guess my general question is a comment on how different this is from that idealized active chiral Brownian particle system.
Yeah, so I'm gonna kind of like, I think we're learning a lot from this. And actually something that something we're recently noticing is the fact that these, when I showed you these particles at kind of like the individual level, they all rotate in the same direction. But it turns out that when we are in this very dense systems where we get these type of waves, either because they interact with the boundary or some kind of, we actually get regions that individuals or regions that they start rotating in the opposite direction. So now we have this picture that it may be that these are bistable particles in terms of spin, so they can either be spinning clockwise or counterclockwise, but potentially they all prefer a particular direction. And maybe the local strains that you get within the system, and that comes from many, you mentioned hydrodynamic, And it may not be relevant, you mentioned it may not be relevant at this stage, but there's also another thing, which is these particles, they have very long cilia. So when you look at the interface, they actually also can kind of like interact with each other at that stage. So there is, I feel like you have many other degrees of freedom within that system that kind of like can of course, give rise to, may not make it very straightforward to just compare that to just a system of particles like that. And in fact, it's been very challenging for us to be able to, like this, we had a set of equations for this, we're trying to do simulations, very hard to get oscillations from these simulations. And I think we think that this is because of the fact that we have these other degrees of freedom, be it tilt, be it the fact that you can get interactions at the cilia level, and that's all can give rise to this type of phenomenon, the plethora of like phenomena that we can observe, yes.
Jose?
Cool stuff. I was wondering, in your experiments, could you crank up the hydrodynamic interactions by adding a viscous goop?
Yeah, that's something we have decided not to touch at this point. I think, first of all, these are, I guess, they live in seawater, so you have to be very careful with osmotic pressure and everything. I think it's something interesting to kind of maybe try to further explore. We haven't, for now, it's not on our radar.
Kind of worms.
Yes.
That was yesterday.
Thank you for the very intriguing talk. I'm curious about in the dispersion relation. Is there an observation of any higher order modes or a prediction of what they might look like if they do exist?
Yeah, I would say that please go to Shiras's poster. Yes. Yeah.
All right, and our last question from Silke.
So just to follow up on what Christian said.
I'll show you a teaser. I'll leave that up here. Yes.
To follow up on what Christian said, so in a way, you can do a null model of chiral ABP systems, which also do local oscillations, but they don't do any of the nice and odd elastic behavior than this stuff says. And this is specifically because it's missing these torque coupling terms. So in a way, you can subtract these from each other and see which part of what you get is odd elastic and which part isn't.
Yeah, I think that's a great idea. Yes, for sure, that's a great idea. Yes.
Nikta again.